Hi guys, welcome back to my channel. Today we're going to be talking about properties of molecules. So molecules have the properties that they do because of their structure. I feel like I say this quite a lot, but structure really drives the chemistry of compounds. So in particular, we're going to be looking at observable properties such as vapor pressure, melting and boiling points, solubility, and we're going to relate that to their intermolecular forces and see how that impacts that chemistry. So the first thing I want to talk about is melting point and boiling point. So when we're looking at a solid moving into a liquid or a gaseous phase, when we're moving from the solid to the liquid, just as a refresh, this is when we have our melting temperature, and then moving from the liquid to the gas, that's going to be our boiling temperature. And so the stronger the forces in between these compounds, the harder it's going to be to break these compounds apart. So we've actually got three of those forces. The first force is the dispersion force, which is the temporary dipole, and that occurs between all compounds. And it's a very weak, very brief force. So how this affects the melting and the boiling point is that the larger the compound, generally the higher the melting and the boiling point. The smaller the mass of the compound, the lower the melting and boiling point. If we have a look at polar compounds compared to just compounds that have dispersion forces, so polar molecules, charged molecules, they tend to have slightly higher melting and boiling points compared to their non-polar counterparts. And that's because of that permanent dipole. And so those attractions are able to form for a longer period of time compared to those temporary dipoles created by dispersion forces. And lastly, hydrogen bonding. Hydrogen bonding out of all of our three forces is the strongest force. And so if a compound has any sort of hydrogen bonding involved, then it's very likely that it's going to have a much higher melting and boiling point. So let's go through and look at a couple of examples. So the two examples I've got here for you are oxygen gas, which is a non-polar compound. And I know that this compound is non-polar for two reasons. First of all, both of these compounds are very, very electronegative, but the difference between them is going to be zero because they're the same. And so based on electronegativity alone, they're both going to be pulling on electrons, and so therefore not polar. The other reason that we know that this compound is not polar is because of that symmetry that it has. So if we have a look at the melting point down here, oxygen melts at negative 218 degrees Celsius. So it's a solid below that point, and then it will turn into a liquid above that point. Its boiling point is pretty close to that at negative 183. So once it gets to that temperature of negative 182, it's going to start to bubble up and then form a gas. So we often see oxygen as a gas at room temperature. Now, if we were to look at the molar mass of oxygen, oxygen has a molar mass of 32 grams per mole, and I just got that from the periodic table. So let's have a look now at water. Now, water is one of those really special compounds. We've spoken about it a few times before, in particular because of its polarity. And we know that it's polar because of the electronegativity difference between oxygen and hydrogen. We also know it's polar because it's not symmetrical. And I know it's really tempting to think that it is symmetrical, but remember that the electrons are really being pulled away from the hydrogens towards that oxygen. So there is an uneven pull. It is asymmetrical, and therefore it is polar. Water also has hydrogen bonding because it's got these spare pairs of non-bonded electrons. When we have another slightly charged hydrogen particle that comes along, because remember this is our slightly positive end, right? And this is our slightly negative end. So when these come along, these electrons can actually bond and almost steal this hydrogen off of this oxygen. And we can actually create lots of these little temporary bonds. And so water acts like a lot larger a molecule than what it actually is in reality. So its melting point is at 0 degrees and its boiling point is at 100 degrees Celsius. And so its state at room temperature is actually a liquid. So that really shows the difference. Oh, actually, sorry. And one more thing to mention, the mass of this molecule, so oxygen is about 16 grams per mole and hydrogen 1 each. So that's going to make 18 grams per mole. So water is actually lighter than oxygen gas based on its molecular mass, but it's actually got a much higher melting and boiling point because of the dipole-dipole and hydrogen bonding that it has going on, whereas the oxygen gas only has the dispersion forces. Now, if we were to compare oxygen gas to a much heavier molecule, so say like a long fatty acid, long fatty acids typically don't tend to be polar because they're made up of those hydrocarbons, and hydrocarbons on their own don't tend to be very polar. But those compounds, because they're larger, tend to have much higher melting and boiling points. So that's how the strength of the intermolecular force can affect the melting point and the boiling point of different compounds. The next thing we're going to talk about today is vapor pressure, and vapor pressure is very closely related to these molecular forces as well, because vapor pressure really is this idea that things are constantly evaporating, right? If you spill over a glass of water and you don't mop it up and you come back to it later, then you'll actually notice that it's evaporated, and in particular on a hot day it will have evaporated a lot more. And the reason for this is because at this sort of surface interaction level, right? So let's draw our little puddle. I'm going to get some nice blue. So let's say I've got my little puddle here, right? And on the surface of my puddle, this is what the interface looks like here. And so one particle can have enough energy to jump out of the liquid state into the gaseous state, even when it's not at 100 degrees Celsius. So what we can see that can happen, it can jump back down into going from the gaseous state to the liquid state, but it's sort of this balance where most of the particles, one by one, sort of jump off or pop off here, and we lose them. And so eventually our puddle is going to get smaller and smaller and smaller and smaller. So when we have really strong intermolecular forces, they're going to be a lot better at holding on to those particles. If you have a look at something like water, water actually takes a lot longer to evaporate than something like acetone per se. So this is something that you can try at home. I would recommend doing this somewhere outside if you're going to do this. But if you go ahead and you spill a ml of water on the ground and then go ahead and spill a ml of acetone on the ground, I bet you $10 that the acetone is going to have evaporated before the water will have. And that's because acetone, it doesn't have that same level of strength of intermolecular bonds because water has hydrogen bonding and it's polar, and it has some weak dispersion forces that are interacting. Whereas the acetone, it doesn't form those hydrogen bonds, and so therefore it can evaporate a lot more easily. So that's how intermolecular forces can affect things like vapor pressure. The last thing we're going to talk about today is solubility, and intermolecular forces have a huge impact on solubility. I think if there's one thing that you take away from these solubility rules is like dissolves like. When I was in high school, I had a chemistry teacher that said that to me, and I thought he was being a bit facetious because I went to an all-girls school for a brief period of time, and he would always be like dissolves like, and I thought, is he just saying that because he's assuming that girls say like all the time? Like, what is he trying to say? Like, I don't get it. And what he was actually trying to say, I realized later, was that things that are non-polar will dissolve things that are non-polar. Things that are polar will also dissolve things that are polar, but non-polar and polar compounds don't tend to mix. So we have a really great example of that here in the form of oil and water. And again, this is something that you can try out at home. If you have ever made dressing at home, all you need is a little bit of vinegar and a little bit of oil. And if you mix the two together, after a while, if you put the container down, then you'll notice that the vinegar starts to separate out from the oil layer. And that's because vinegar is acetic acid, so that has the formula CH3COOH. And because we've got these electronegative groups, they tend to pull the electrons towards one side of the molecule. So we actually do have a slightly charged compound here. If you compare that to something like oil here, or these long fatty chains, or butter or something like that, with carbons and hydrogens, the electronegativity difference of carbons and hydrogens is actually pretty close to each other. And so when we have these two compounds that are put together, it's almost like these charges repel the non-charged non-polar compounds, because basically these guys are only going to want to find other charged compounds, whereas the non-polar, if they come across a charge, they're going to be repelled by that because they don't have the opposite charge to be attracted to it. So that's why they end up separating out, is because of those differences in their polarity. Similarly, the shape also affects the solubility. So if we have something that's like a really long straight chain, so something like I've drawn here, and we have a chain that's got some crazy branches sticking out of it like this, well, the crazy branches are going to be a lot harder to sit closer together compared to these really flat chains. And so they will also tend to be a little bit lower in their melting and their boiling points, but they will still dissolve into the non-polar compound because this shape can still just pop in and sit nicely on there, and they're not going to repel each other. So that's how intermolecular forces and the structure of compounds affects different properties. So we've spoken about melting and boiling point. So the stronger the intermolecular force, the higher the melting and boiling point. We also saw how it affected their vapor pressure, because the stronger the intermolecular force, the more likely it's going to hold onto its particles at that surface level. And so the stronger the intermolecular force, the lower the vapor pressure, so the less vapor that it's giving off. Lastly, we've seen how the intermolecular forces can affect solubility of compounds, and the takeaway from that is like dissolves like. So polar compounds dissolve polar, and non-polar compounds dissolve non-polar compounds. Alrighty guys, that's it for today's video. I will see you in the next one.